Well, good morning, everyone, and fantastic to see you here early in the morning. Well done. Who actually normally comes to an 8 o'clock lecture? Like, who normally comes later in the day to the... Oh, no, okay, this is 8 o'clock. Okay, obviously some of your peers are in calculus, so we're going to record today's presentation. And if you've got a friend who couldn't be here, obviously we'll be making that available. You know what this is? It's a masterclass. So obviously next year we'll be doing an advanced version of Data 1001. It'll be called Data 1901. And so this year we just have a sequence of 4 masterclasses just to give you, I've been saying in class to you that obviously we're giving you authentic data stories, but it would be even better if you could meet the researcher working with that data, yes? And so that's the point really of these masterclasses. So this morning we're going to hear about half an hour from our presenter. And then as she's talking, I want you to think about maybe just one question you might want to ask her. And it can be about the specifics of what she says, or maybe just something general about how to get into that field, or, just stuff about her development up to this point. So I'm going to introduce you to our presenter, Dr. Emi Tanaka. And I'm going to ask her 3 very important questions just to start off, just as we get to know her. So first one is, Emi,
yes.
KFC or McDonald's?
Oh, Hungry Jack's.
Hungry Jack's? Oh, no.
I used to work at Hungry Jack's.
Okay, what about Pepsi or Coke?
Coke.
Coke, okay. And I know the answer to this one, I think. PC or Mac?
Well, I've got a Mac here, and that's my laptop, so I'm definitely a Mac person. Got even an Apple Watch as well.
Good. Well, thank you for joining us this morning. We look forward to your presentation.
Sure. Turn on the lights, off the lights, because is that better for you guys? Yeah? And I will just... Yeah, okay. So hi guys, thanks for coming for so early in the morning. So I'm going to talk a little bit about my history first, and then I'll get into showing what I do. So my name's Emi Tanaka, and I'm a lecturer in statistics at the School of Mathematics and Statistics at University of Sydney here. So, you see lecturers, I think, and most of the time you think they do a lot of the teaching. So I do teaching, but on top of that I do research as well as service work, which may include being in committees, sometimes doing outreach work, and so forth. So before I actually go on to tell you about what I'm doing, I thought I'll go and talk about how I came about to become a lecturer in statistics. So this is a bit of a animation where you can see that's me over there, and this is the path. Now over here is my icon, and rather than, I actually used to have this as a list, but I thought I'll make it a little bit more colorful, and these icons all represent a certain subject area. So maybe you can guess. So here, what you can see is arts. This one is chemistry. Anyone can guess this one? Yeah. Yep. Yeah, so English basically. And you can see this is it's in high school. Did you guys all go through a high school at New South Wales? Yeah, pretty much. Okay, so you got to do 12 unit credit points. It's the same. I went through a high school here. So I had to do 12 unit credit points. And in that case, what happened is that these are the subjects I've actually taken. And you can see mostly it is science oriented. The only one out being the art one. And art is something that I actually wanted to be. Like when I was actually a child, I wanted to grow up to be an artist. But I was fairly okay when it comes to mathematics. And then realistically, in terms of job, I thought it's better that I actually go do more science-oriented subjects. And I thought I'm doing fairly okay. So actually, when I got to year 12, I did drop it. And so these are the subjects that I ended up doing. And I actually did, instead of doing extension 1 mathematics, I upgraded to doing extension 2, which allowed me to drop the arts one. Okay. And then, so I got to uni, and when I got to uni, I did Bachelor of Science, majoring in mathematics. And in the first year, so you do have to take other subjects just beside mathematics. So I did physics, I did chemistry, I did also software programming, and this was the first time I started doing software programming. So it's a really standard set of really science subjects that you would do in your first year. But so what happened though is that I didn't really like the lab work that was involved in physics and chemistry. So it really came from the part that, I just wanted to avoid those 3-hour labs. So I just dropped it and then basically concentrated on mathematics. And this one here represents statistics. So as I went through, I decided to do statistics in honors, and then I picked up in my PhD, doing PhD in statistics as well. Now, the area that I chosen to do statistics was in bioinformatics. So that is applying statistics in the biological area. So over here you can see that I picked up biology, and this was actually the first time since maybe back in year 9, 10 that I actually started picking up biology. Now, afterwards, I finished my PhD and then I got a postdoctoral position. In that one, I now was applying statistics in the agriculture area. So this is where, after a PhD, picked up ag in statistics. Now, as time went by, basically that part of component actually grew up. So now most of what I do predominantly is that I apply statistics in agriculture. And behind the scenes that you will actually, I am using mathematics, I'm using a bit of biology, and also a lot of software programming. So what do I actually do in terms of when it comes to the work? Well, before I actually get into it, I thought I want to explain a little bit more background. Now, first of all, you see here like pictures of apples that you can buy at Coles. So the images are courtesy of Coles. Now, do you have a particular apple here that you like? Who likes Pink Lady? Yeah? What about, who likes Granny Smith? Yeah. Royal Gala? Fuji? One of those? The delicious apple? No. Oh, so Pink Lady seems to be quite popular. So one thing you notice about here, and to showcase this, is that here you see different kinds of, they're all apples, but they're all somehow different, aren't they? Well, so if we get into it, now they're all different and they have some kind of traits. Now I want to explain a little bit about possibly what farmers actually need to consider when they're actually growing certain different kind of varieties. So what you see over here is, let's say that I start off with a set of carrots. And so I've got this kind of population, and they're rather really different kind of carrots, which a lot of them are quite browny. Now, maybe perhaps, just like you guys who liked Pink Lady, or some of you guys, you might actually like a certain type of carrot. So over here, I might like the one that is actually on the right. So you might select that and basically carry over to make more of carrot based on those carrots that you like. So you select it, and then you're going to breed based on that. Then you get a new set of population, right? And then that set of population, because you use those as you only bred from the carrots that you like, are going to be more similar to that carrot that you bred. Now again, you might actually think about, okay, look, I like that particular orange one rather than the dirty orange ones. You might select that and then breed up on again. So keep on repeating it, and you keep on selecting the traits that you really like, you want to optimize for. And then so you carry forward, and finally you might have a product like this where you get a carrot that's orange, quite big, and has other traits that you might like. So this is a real picture, and this is the reality of selective breeding, where you can have a big difference, where this is over here is a carrot that's basically just grew up in the wild. There was no selection that was taking place by people. And this is the one that people interfered. They bred the ones that they want and continuously conduct their selective breeding. So you can see it makes a huge difference by actually going through these selective breeding. And in fact, it's really necessary part of what we need to do if we want to continue really living, because we cannot get enough food without having some sort of selection. So another one here, so not just to be all plant-based, but let me just showcase an animal one. So this is the weight of the chicken back in 1957. So we got about, when it's about 56 days old, is about a kilo. In 1978, so over time, you do a lot of selection, and the most likely thing is that you want to optimize for weight. As a farmer, you probably want to be able to get more meat out of the chicken. So by 1978, we've got about 2 kilograms of chicken, and then 2005. Now this is the state you can get up to. Of course, here we're just optimizing for weight, but keeping it simple, that could be dangerous. And that actually happened, I think, during the 90s. They optimized too much just for the weight, and what happened was that the chickens were born really fat, and then what happened is that they developed heart disease. Their legs were really weak because they couldn't support their weight. So you had a lot of unhealthy chicken. So there was a moment where then they realized that they should really try to make sure you optimize for other traits as well. But so then it becomes a consideration of optimizing for really not just the weight, for other traits as well. And then, but it becomes a little bit more complex if you're trying to optimize more than one trait. So, but this is an example of really the animal breeding side. Now, I can summarize the aim of really when it comes to selective breeding. And that can be really summarized using just one equation, which is that we want to increase genetic gain. Now, genetic gain, if I define it more formally, is that it's going to be the difference in genetic performance over time. So I want you to keep that equation in mind, and this is essentially everything I do is linked to this, that I want to try to increase genetic gain in my work. So a few things I've gone through and done. Not sure, so we've got about 50 minutes to go, and I don't necessarily think I have enough time to go all of it through this. So I'll just briefly describe a little bit and ask you guys which one actually do you want to see. So a few things that you can do to really increase genetic gain. One, which if you're doing data 1.0.1, if you improve experimental design, that does help. The other thing is actually improving prediction of the genetic performance. And so later on, if you're doing data 1.0.1, you'll learn about really simple linear regression and multiple linear regression possibly. And so it's linked to that basically. So the modeling part will help in terms of increasing genetic gain. Now, picking up a certain domain-specific knowledge helps also into really answering that overarching aim as well. We do also have peripheral issues which we need to solve in order to get better genetic gain. So this is actually more indirect way of actually helping genetic gain, which is to improve computational performance, especially with the advent of more and more bigger data. We need to have a way of doing fitting models in a reasonable amount of time. And there could be more solutions, and they indeed are, not just based on statistics alone, or even you could come up with more creative ways, and perhaps you guys might be one of the people who might come up with even creative, like out of the box ideas that could actually integrate many things together to answer that overarching aim. So maybe I have time for about one or two out of these ones. Do you guys have like a preference? You want to learn prediction? Okay. That's the second boring one, but yes, I will go through it. And then, is there like another one, just in case I have time? What? Experimental design? Okay. So let me go through, because they're in order, then I'll go through the experimental design and the prediction one as well. So this is explaining experimental design in a really, really simple way, and I'm pretty sure Dai is going to go through experimental design in Data 1.1 much better than I'm going through. But let me still go through it. Okay, suppose like we got those 5 apples that we saw earlier, right? And we got a block of land. And so what I'm going to do is plant these 5 apples onto the land. So one row, I'm going to put the Fuji apple, the next one, the Pink Lady, Red Delicious apple, Royal Gala, and then last one in Granny Smith. So now I grow it, and I get an apple growing. And then what I'm going to do is harvest it, and let's just say that as a farmer, I might only be interested in getting big apples. So what I'm optimizing is just weight alone. And I'm just trying to keep it simple. I know there's other factors that take into account when it comes to apple, like, sweetness, the sourness, and so forth. But for the moment, let's just imagine that we only care about the weight of the apple. So harvest it, and I look at the average weight. So looking at this average weight, and you have to make a decision, let's say, as a farmer, which variety you're going to plant. Which one will you go for? Yeah? So Granny Smith obviously here actually has a much higher weight. So you'd think about going for that one. But what I didn't actually tell you beforehand is the condition of the actual soil. So behind the scene, what happens is that the first 4 rows actually had a very dry land, and then the last row was actually quite well watered. So the result you actually see is a result that just the condition was a lot better for that row as compared to the other 4. So this begs the question is that if the conditions were equal, so if the other lands were actually as well watered, then would those other apples have done better in terms of the weight? The other thing about it is that maybe as a farmer, my farm might actually be in a very dry land. So if I actually plant this Granny Smith apple there, it might actually not do well, because this is a result of actually having a soil condition where it's well watered. So in that sense, it's going to draw a wrong conclusion out of this particular data, because I haven't taken into account other sources of variation that comes into play. And in this case, it's a flawed experimental design, because I have the condition of the soil and the variety of the apple confounded. So this is a more simplistic sort of explanation when it comes to the experimental design. If you come on to do third year in statistics, we will talk a little bit more of complex designs. But a lot of the basic foundation can really be simply explained by something like this. Okay, so the next one was a prediction. Okay, so this one, I'm going to try to put it really simplistically as I can, which is that here what happens is that I observe some kind of trait, and then any observable trait is, I'm going to refer it as the phenotype. Now, often what you're interested is actually knowing what the effect of the variety is. So that could be potentially removing any sort of random sources of error. So essentially what happens is that you only see phenotype, for example, the yield, the flowering time, the disease status, and so on. But what you're interested in knowing is the variety effect, or I synonymously call it the genotype. So this becomes a modeling question. Here's something that I don't observe, and there's a trait that I observe. Can I try to predict that unobservable trait? And if I can, I want to get that prediction as accurate as possible. So this is the core of the research that majority of people do in this particular area if you're statistically oriented. So we fit really a lot of complex models, and we always assert that we are doing better than that before. So it can get as complex as this, and part of what I'm doing here in equation form is that I'm trying to take into account that if I got plot of land, if the varieties are sitting next to each other, the performance will be more similar, or the residuals will be more similar because the soil that they share are similar. So I'm taking into account that they're not completely independent. They're sitting here spatially together, so somehow I have to model that spatial dependence between them. I could have other sort of sources of variation. Got to take into account when it comes to a farm, there will be tractors that move around, and that could cause a certain variation that I end up seeing in terms of the yield. So these are the part where, when I get a set of data, I have to go and try to remove any sort of signal that might come into place in order to get a better genotype prediction. So equation form, normally you will see it if you see in papers written out things like this. And so this is what we call linear mixed models. And so if you do third year statistics, we do teach about this. We can always make it better. So this is a component of research where I do a lot. So in this one, what I'm talking about is then I'm going to model it such that, in this case, the varieties that I'm looking at, normally what happens is that treatments are considered independent. But the thing about is the unique thing when it comes to variety trials like I have is that treatments could be related because they may share the same father, same mother, or grandfather, and so forth. And so what happens here is that I'm trying to model the fact that they're not completely independent. They have some kind of latentness together. So let me try to capture that and put it somehow in the model to capture the relatedness between the varieties. And that should give me a better prediction when it comes to the genotype effect, because my model should reflect a little bit more closer to what happens in nature. And then other further things that can I do? Here what happens is that most of the time when trials run, they run trials across different locations. So these are called multi-environmental trials. And so in this circumstance, what happens is that a same variety can be planted at different locations. So what I can do is to try to borrow information from other trials in order to get better prediction. So there's actually more things in this area, and I can talk more and more about it, but you do need to know, I guess, a little bit more about the modeling part. I won't talk more into it, just to give you a gist of idea that this area is in particularly a big research area. And people always talk about different kinds of models, which they always assert that their model is better. But I think in that sense, George Box's quote actually fall very well into this, is that all models are wrong, but some models are useful. Now, I assert, and I'm going to have a different quote, that all models are wrong except for mine. And this is what, I as researcher, I always try to assert. All right. So I will move on. Oh, this one. Oops. I should click on this and this should skip. Okay. So I want to show you a little bit of key outputs that I have from my research. So I tried to remove a lot of the um, details because I don't want to just boggle you guys with details, but more give you guys an idea what sort of output comes out. So I tried to get the most visually appealing kind of outputs I had. So in this one over here, what you see is that it was a paper I published last year about a methodology. And in this one, what happens is that, so to give you a bit of a gist, what they get is that they looking at the starch. And so what they want to do is to try to quantify the different types of starches within a sample. And so what you see is that you see this trimodal kind of distribution that you see over there. And so to quantify it, one of the things that we suggest is to really fit a mixture model. And so I try to show mathematically why this is better. So the paper has, and I'm very happy about, was the actual mathematical part, although those details are usually put aside. And so the main thing about was that there's a tool that people can use. And so we got a tool called Granular, which is an R package as well as a Shiny application that you could play around with, which allows you to fit these mixture models and easily get quantities that you need. The other one that I wanted to show you, which was more of a recent work that I did, was that I got invited to a talk last month to a plant breeders meeting. And then so I spoke to them about the analysis and the results that for the data set that they're interested in. And let me just show you a little bit about this one. So you can actually play around with this if you want as well. So you can go to the particular website up there and play around with it. So this is for really people who are non-statistical audiences. So try to have it as visually appealing as possible so that they get to play around with their own data set and make informed decisions. So here what happened was that I had 45 trials, and then altogether I had a little bit more than 1,500 varieties. And then these are all planted around Australia over many different years. So here what happens is that they can have a look at things like distribution of the yield across the years at location. And so part of what was nice about this tool is also that you can actually have a look, say that if you want to look at a particular variety, you can actually have a look at where they've been planted and what was the actual yield that you got obtained from those varieties. The other things like field layout. So this is actually the field, and what happens is that you can zoom in and have a look a little bit more in details. So they really appreciate some tools like this. And the other one was, this is the one that hides a lot of the statistics, but this is the part linking to the prediction part, where it's gone through some modeling and you get the prediction and they get to see the performance of the top 5 varieties. And to give you the gist behind this is that these are trials where they have 2 international centers, one in Mexico, the other one in Europe, and they're very dry land areas. And what they do is they import varieties from those areas into Australia and test it out in Australia. And so what happens is that it's colored here according to the sources. So the green one you see is the Australian varieties, whereas the blue one is one that's from Mexico, and then the red one is one from Europe, dry land area in Europe. So what they're trying to do here is that if they're plant breeders, what they're interested is to try to find out which variety are they going to take and put it in their breeding program. So something like this is that you can see here is that getting the Mexican variety might be a good idea, because you can see, at least for North Star, because you can see most of them are performing better than the Australian checks Australian varieties. So it's tools like this is part of my research to communicate these ideas so that other people can really make informed decisions when it comes to their own data set. One thing I do want you to note is that, now you can see how like when it's loading, you can see the loading screen there. And so that was actually, I had to program that in. So it's like, oh, while it's, waiting for the graph to load, have some kind of loading screen there. So this is something that's really more like a hobby thing, which comes to the last one, is that, if it goes, there you go, is that there was a package, but then I didn't like the fact that I can't customize it. There were only like a standard stock loading screens. So it was a completely hobby project where one of the weekends I basically decided that I'm going to make a package myself, and what happens is that you can customize the loading screen as you want. And so I thought what would be nice is to actually share this to the community. So because I like it, I thought maybe somebody else will like it as well. So I put it up in a package, posted, tweeted about it, and what happened was that it went really viral. And so what happens is that this got over 300 likes and over 70 retweets. And I have to say, so like you need to know the comparison to see how big of a measure it is. When I tweet, I maybe get a single digit like. So this is like about 300% more than the usual case. So that was a little bit of a fun weekend thing. But you can also see that it's not really, I think it's not just about really the data, but an analysis part, but also about how you communicate your results. And it could be completely not about the main thing, something peripheral. And so this is just an example of that. Okay, so going back to the title of the talk, like what is in store for statisticians tomorrow? So which is what is in store for you guys tomorrow? Well, that is actually hard to say because nowadays you're really demanded to do computational tasks. Do you go do mathematical? Do you do more theoretical? Should you be doing applied? Should you be picking up domain knowledge? Should you be working in communication? Should you be working in visualization? There's really a lot of things you can do. And so it's really hard to say that what's going to happen tomorrow and what's the best technique you should be picking up on. But I like the quotes that mighty oaks grow from little acorns grow, which means that, you can just start off small and then great things will grow from there. So I think just looking at my past, I really started off with like a little bit here. Oh, I like mathematics and statistics, and let me go on there. Like it's really just small things I did here and there, and then just grew up from that way. So I think for you guys, what you want to think about is just to start where you can, and then just don't give up. Just keep on going, and you will grow to a mighty oak. So, all right. So if I'm really, I like visualization a lot. So if you come across something nice or you make nice plots, feel free to actually get in contact with me, tweet at me if you like, and then I'm quite happy, to be able to see what you guys are doing. You guys are one of the first cohorts to be going through a data science program. So I'm sure, a lot of us, not just myself, are really interested in knowing what you guys actually will become afterwards. So also, before I finish up, I do want to say that, Sam and Di over here has actually done a lot when it comes to organizing the data science programs. You probably guys don't know, but really they drive when it comes to the program. I just come here to talk. So if you don't mind, could you give a hand for them? Thank you.
Okay, let's give Emi, first clap now, and then we'll ask her some questions. So that was fantastic.
Yeah.
Thank you. Many people think my lectures are boring, but anyway, I'll put up with that. Very good, Emi. I'm going to ask you one question, and then we'll throw it open. You can ask Emi anything, really. Just ask her, could be about her high school stuff or about where she's got to now.
Yeah.
But can you just give us a little bit more, that little quote that you gave us about all models are wrong? Like in some fields, that wouldn't be the case. Like, why is it in stats? Can you just explain that a bit more, that every model ultimately is wrong, but we want a useful one?
Yeah, no, that's a good question. Well, I think ultimately it comes down to is that, models are trying to pick up the major signals. And like, if I want to say model your life, let's say, I need to know every single detail about your life to capture that, right? So the thing about it is that most of the time we don't actually measure those covariates that we need to be able to model things. So it's always going to be an approximation. There is some covariate that we have missed because we don't keep track of everything out there. So that's why I don't think ever a model can be capture the natural system perfectly. And that's where I think you find that all models, it's an approximation. And you want to try to get the approximation as close as possible to the true natural system. Yep.
Is there a Python port for Shiny?
There's a Python one called Dash, which is a little bit similar, so you can give that one a try.
Yeah.
Yep.
So you mentioned at the start with like visual art and stuff like that, you did some sort of art. Has that helped with your with what you later on journey as well, or is it
So I would doodle a lot, and I was never really serious into art. It's one of the reasons I dropped, because I didn't think I will be successful as an artist. I do think that I tend to be very visually oriented. So when it comes to really slides, I'll do like animations, or I really bling it up. So maybe that's affected me that way. So I think in some ways it helps your creative side, and so it's also more of a hobby thing as well. So having something aside from just your main work is good for possibly relaxation, creativity, maybe possibly mental health as well. Yeah.
I have a question. So you mentioned about prediction.
Yeah.
So usually, according to statistics and the real result, how much can be the difference?
So with real data, we don't know what the truth is, right, at that moment. So the thing about is that I do simulations where I know what the truth is, and then I do compare with that. And so that's an artificial kind of setting, but under that setting, it's actually pretty okay. So I'll get accuracy of like ranging from like 0.8 to 0.9. So I do find it's okay. And the other thing about it is that, generally speaking, there is some trust in certain types of models, because with agriculture, we always, like every year we do a trial, and so the following year you can kind of see some of the results. And so what happens is that there's more fine tuning when it comes to the model as well that way. So so it gets better, but this is very domain specific, I think, because the models that I build really does require domain knowledge in order to build them. And accuracy-wise, it can get quite good. But you got to consider the fact that when we do experiments, these are really well-controlled experiments, and that's something that is very much embedded within agriculture, because this is actually how experimental design came about in statistics. That they all started off really with agriculture first, and because of that history and the fact that we can control a fair bit of things, makes us able to get more accurate results. When you do look at things in today's more modern world, with maybe possibly getting data from, say, your mobile phone, computers, they're a lot more noisy. So it's probably a lot more harder to model and get especially for human data, it tends to be the case because I think people, it's very hard to control people. They don't sit still, like plants. They move around. They like to do other things. So there's so much noise that gets entered into the data. So in that sense, I think your accuracy is gonna generally get lower.
Yeah. So why did you choose bioinformatics, and what would inform your decision if you were to make that decision again?
So it turned out to be a good decision, I think, because I think nowadays bioinformatics has grown as well, especially with the advent of new sequence technologies. So it was a little, I don't really think, and this is actually an issue, and I do want you guys to think a little bit more than I did, because all I thought was, I'm going to do mathematics and statistics because I like it, I don't want to do a lab. And then the thing about it is that I also like the computer programming, so then I thought, I'm going to do a computer programming kind of thing when I do honors. And so what happened is that that time we had a new staff that was joining the faculty. And then so he actually came from a computer science department. And so I wasn't really aware that he was really in the bioinformatics field. It was more that, he would, and I haven't actually met him. So I knew he was coming, I heard about him, and because he came from computer science department, I thought, I want to do this. I want to go to him and then learn a little bit more programming. So I got into it just because more like on a superficial front. And then it turned out that he was into bioinformatics. He became my supervisor, and then we carried on to PhD. So I did not plan at all, and you can see I didn't actually pick up biology until that time. So initially it was a little bit difficult, but now I think having biological domain knowledge does help, because it's really, if you do like a medicine field, or even agriculture, we do use a bit more DNA technology now. So in that sense, it was, I think, a good choice.
Was there any other fields that you thought might have been interesting?
I did like software. So initially you saw me pick up software in the first year. So I didn't want to do more of that, but again, what put me off was that I had a pretty bad experience in group work in my first year, where what happened is that my group never turned up, and then I just thought, this is why I went into it's a bit sad, but mathematics statistics, I thought, oh man, people they don't come to do the group presentation and whatnot. I don't like this. I'm just going to do mathematics statistics where I'm just lying to myself. Don't do what I did, because you are ultimately going to do group work in the future, and I do so much collaborations now, so that I wish going back I did do a bit more, try to do more interdisciplinary kind of communication. So computer science would have been one area that I would particularly have liked to actually gone in a bit more. But I think now it's kind of merging. Like in statistics, I do a lot of programming. So in the end, I think it would turn out to be quite well. Yeah.
So you've got a list of like different types of knowledge that you might need. Out of those, which has been most useful to you?
So I think now there is a boom for really what's called data science or even statistics. And then, so I think this is something that is going to continue for the future for quite a foreseeable time, because we're starting, we get so much data, we need to make informed decisions, and I don't see that will change. So I do think this is one of the things that really is helpful. I think just besides the hard skills, I think soft skills are quite important, and it's probably not as mentioned as much when it comes to the hard sciences. Your ability to communicate, your ability to build network and trust with others. Those skills are, I think, really the core of things when it comes to, I think, a lot of jobs, because you do need to talk to people and build those work together. I think what helped me, I think, along the way, which is that, and I think it lies down to the core of what statistics is about, which is that statistics is using to help other people understand their data. And so it's not, the focus is not, about promoting yourself per se. And so, my parents had a principle, it's like, try to do something for other people. And so that sort of principle actually, I think, helped along the way, that like when I do things, it's more like I'm trying to help other people understand the data. And that sort of thing actually helps to communicate with other people. So I think it's more the soft skills that actually is the foundation of when it comes to disciplinary work.
Another question, just because you mentioned about this quite a few times, like with technology and because data science is so close to it.
Yeah.
In your experience as a statistician, like how has technology changed how you worked and what do you see in the future?
I think the thing that has rapidly changed is that there's more demand in people to do create outputs, like the Shiny app. So there's more push for having a front face where we communicate better. And so you'll see that I think in the last few years really that there's more emphasis on visualization. So I don't know if you came across ggplot already. So there's sort of like having a more appealing visuals visualization, Shiny app, where people can do interactive, either interactive presentation or interactive session with their data. I think this is how technology really is being changing.
I have another question. Now, machine learning and neural networks is quite popular.
Yeah.
So, are you working also in this field, and can this field also help statisticians to improve the service and, can eventually can statistics be done? I don't say completely automatically, but in some extent, that can it help? This technology can it help statistics as well?
Yeah, so I mean, it depends on how you exactly define machine learning, because all the prediction and the modeling that I do can be classified under the bracket of machine learning as well, because I'm predicting as well. But so more people might associate machine learning nowadays more with things like deep learning, so neural network, random forest, but so at the core of it, I mean, machine learning, I just see it as still a subset of really statistics. And so the other part you're talking about is whether certain, so if I get it right, it's like certain autonomous kind of statistics, will it help? Or would you guys not have a job, I guess, is also the other question. And there's always people talking about this. Like, I mean, a few years ago, I remember people talking about how, like, maybe statisticians will become obsolete because these things will automatically be done. I think as society progresses, I mean, this is my thought, is that there are some things that are going to become obsolete because they will be automated. But it's not something of a concern ever to me, because I always believe that so long as, like, it doesn't matter what profession you go to, so long as you're the top percent of people, you're always going to have a job. And so that's why, so long as, I think it's more a matter of you try to perform yourself better, and then you'll be okay. And then automation to some level, I think is good if you have there are some routine things which I think does actually help to elevate time away for you to be able to do other things that are more higher level that machine cannot do. And there will be always something a machine cannot do because they're only trained on a certain training data set, and essentially they're only able to tackle something that they've seen previously, but not something that they never seen before. And so that's where I think still a human interaction is needed. And you'll
give Emi a big thank you.